So this problem is asking us about a transformer, and it gives us that the transformer starts at a substation at 15,000 volts, and once it gets to the neighborhood transformer, the voltage is stepped down to 120 volts. And so yeah, the thing we're dealing with here is a transformer. The book explains that the way transformers work is that the left coil, which is that primary coil with the primary current, primary voltage, it has N1 turns and it's driven by an oscillating voltage, and the magnetic field of the primary current follows the iron core and passes through the right coil, which has N2 turns and is called the secondary coil. And that alternating current through the primary coil causes an oscillating magnetic flux through the secondary coil, which then induces an EMF. And that induced EMF of the secondary coil is delivered to the load as the oscillating voltage that you get on the other side. So essentially, in much simpler terms, our voltage gets stepped down or stepped up depending on how many turns the contrasting sides of these transformers have. So there's going to be that direct relationship that you can see I've written down. V2 over V1 equals N2 over N1, with N being the turns and V being the voltages. And V1 is that starting voltage, and V2 is the ending voltage. So we do have enough to immediately solve this. All we have to do is use that equation and plug what we know in to figure out how many turns is going to be in the primary coil, because that's what A is asking. Giving us also that the secondary coil has 110 turns. So all we have to do is rearrange that equation, solving for N1, and plugging in what we know, and we get a total of 1.4 times 10 to the 4th turns. So yeah, that's a lot more turns, as you can see, 1.4 times 10 to the 4th versus 110. So that's how those numbers work out to get that drop in the voltage. Part B explains that no energy is lost in an ideal transformer, so the output power from the secondary coil equals the input power to the primary coil. Suppose a neighborhood transformer delivers 210 amps at 120 volts. What is the current in the 15,000 volt line from the substation? So as I said, P out is going to equal P in this case. And we know that P has always equaled current times voltage. So since we know the current of the input is times the current of the voltage has to equal vice versa, the current of the output times the voltage of the output, we can just set those two equal to each other. And the only thing we don't know is that I1, which we're being asked to solve for. So that's all we have to do, rearrange the equation to get that I1. And then when you plug in the numbers for this, you get I1 equals 1.7 amps. So you can see that with a number that's so much larger of 15,000 versus 120 volts, you're going to have to do it's going to be very much represented in the math, where our current is much, much less in the PN to the primary coil. So that's pretty much part B. I think that's it. This problem isn't too bad. The thing you have to be careful with is just getting your I2s and V2s straight, because you want to make sure that you're plugging in the correct things in the correct places. Conceptually, it's not too bad. Just make sure that you understand how transformers work. But yeah, other than that, not too bad. Thank you for listening.